Let me write this in a better way. Oops. Okay? So that summarizes and there is even another one. With respect to some basis. Okay? So that is all. The whole of the story around diagonalization, around eigenvalues, their eigenspaces, their sum, that's the whole story. Okay? And we actually, while I was doing this, I actually gave a complete proof of all of this. I actually showed that A actually implies B, okay, and I actually showed that if you have B, then C is obvious, and then I showed that C actually implies A, and using properties of matrix multiplication, this turns out to be equivalent. Okay? So, this is all the story about diagonalization, eigenvalues, and eigenvectors. In the next class, we will look into real symmetric matrices, which are even better, and inner product spaces. So I'll stop here. Now, if you have any questions, it's already 6. So shall we disperse for 10 minutes and join after 10 minutes? Okay?
Good evening. How are you?
Good evening. Yes.
I just see you on the videos, so this is my first time coming here. Yeah, so I'm just the first time doing MAT2611. So I wish I got the lecture at the beginning, so
Okay.
yeah. But hopefully, I suspect that you'll be doing another lecture maybe next week.
Yes, this week. Let me come back and say.
Okay, okay.
Yes, let's resume all the centers. Yes, queries.
I don't have a question today, but I don't have any question today. I assume you're still live.
I think so, yes.
Yes, on my side, I don't have a question today.
Okay. Any other center?
Sir,
Yes.
you know, for problem 4, G, nah?
Yes.
F at x and g at x are not bijections. Yes, f at x and g at x are not bijections. But and they say, how does the second part compare with the first part? I don't know how they compare.
What is 4D saying?
Oh, okay. It says given a finite dimension vector space V and linear transformations F to Fg with domain V and codomain V, show that G of F is bijective if and only if both F and G are bijective. So then that part I think I understand, right?
Okay.
But then the next part says that let Rx, you know that polynomial thing?
Yes.
That polynomial thing
Yes.
for F and G is the domain and codomain.
Ah,
Okay.
yes.
Be the linear transformation such that
Yes.
be the linear
What is
transformation. Excuse me, sir?
Yeah. What are F and G? What does F do?
F is just nothing. Oh, F at xn is equal to
This
x
is?
to the power n plus 1.
Good.
And g at x is g at xn, sorry, is equals to x to the power n minus 1.
And what is G of 1?
G of 1. Okay.
Yes.
If x to the power 0, x to the power 0 is equal to 1, and x to the negative 1 is understood to be 0.
Ah, okay. So, this is 0. Okay? Now, remember, this is a basis. This is a basis. So, when you are saying it's, so suppose let's take a polynomial. fx takes this polynomial 2 right, and gx takes this polynomial 2 clear? Clear? So this is by that linear extension principle. This has to be the linear operators. Okay, good. Now let's see what is G composed F. G composed F, so you go here, come back here. So G composed F takes Px to Px. Not really. Not really. It takes, I think you told me something. Is this this or this one? One minute. No, you're right. So G composed F, if you see, so you know its action on the basis is enough. So let's look what is happening on the basis. So first when you put me to F, this goes to and G then takes me to so therefore G composed F is the identity. But
so how do we know that G composed F is the identity?
well, if it takes, if you have a relation which of the basis elements, G composed F takes 1 to 1, x to x square, x 10 to the power n to x to the power n. It must take any polynomial to itself, right? By the same logic of extension. So G composed F is the identity. Okay? Now let's see what is happening. G composed F is the identity, but I know from set theory that this should say G is surjective. And F is injective. But G is definitely not bijective because 1 is in kernel of G. Okay? So the kernel of G is not trivial, so G cannot be injective. And F is not surjective because again 1 doesn't belong to the image of F. So F is not surjective. Okay? And why is this happening? The reason is finite dimensionality. If the vector space V is finite dimensional, that rank plus nullity theorem tells you being surjective is same as being injective is same as being bijective. Okay? That's all the story. That's the power. That's the control. So let me say it again. Suppose V is finite dimensional, then I know that dimension of the kernel of F plus the dimension of the image of F is equal to the dimension of V. This is the magic. So let's see. Assume, so let's take three statements. G is surjective, or let's take two statements. G is injective. G is injective immediately tells me that dimension of kernel of F is 0, which immediately tells me that the dimension, oh, sorry, not the F, why I am saying F again when I wrote, okay, so this says the dimension of the image of G is equal to the dimension of F. And this is the same thing as saying that the image of G is equal to F. Because there exists only one subspace of any vector space whose dimension is equal to itself. On the other hand, this statement is same as saying G is surjective. Okay? So you see, again. Sorry. That's just. So a linear transformation is on a finite dimensional vector space is surjective if and only if it is injective, if and only it is bijective.
Please repeat that.
So this tells us a linear transformation on a finite dimension. So surjectivity automatically brings along with it injectivity. This strong equation. This equation is very strong. If dimension is not finite, this equation doesn't hold good. Doesn't make any sense. So everything fails. Okay? Everything fails. I mean to say, the example given tells us that it is not going to be true. Okay? So the statement is actually if dimension is finite, then surjectivity, injectivity and bijectivity of a linear transformation are synonymous. They are the same thing.
So sir, technically speaking, right, you can say that if something is finite dimensional, then it's definitely bijective.
No, I didn't say so. There could be linear transformations which are not surjective and hence which are not injective or bijective. So here is an example.
Or they could be subjective.
Yes, here is an example. It is definitely not surjective.
Yeah.
So it is not bijective or injective.
So why is it not bijective? Why is it not surjective? Because it should be on.
Well, what is? Give me a member of R2 which comes to say 0, 1.
But sir, isn't the definition for surjective that every element of Y must exist such that there's an element of X? Like, it doesn't need to be all the elements of X onto all the elements of Y. It just needs to make sure that all the elements of Y are.
Correct. Correct. So give me an XY such that P of XY is 0, 1.
Oh, yes. Oh, okay.
Yes.
So it's not surjective, bijective, or injective. So what is it?
Well, it is just a linear transformation.
Oh. Okay, sir. Thank you, sir.
Thank you.
Sir?
Next. Yes.
I have a question. Here's a question here. It says, without any further computation, state why the following statement is true. A product of two square matrices is invertible if and only if both the square matrices are invertible.
Yes. Because you told me right now that if you have G this, then you told me that G composed F is bijective. If and only if G and F are both bijective. So that's why.
Isn't the same?
That's why.
It's not the same. Oh, so it's not the same leg. Okay, let me ask.
But you know that every linear, every square matrix is equal to, for some F. So, therefore it is done. That's it. So where is the computation? You don't need any computation.
So the statement is true.
Yes, and here is the proof. You don't need any computation.
Okay, sir, thanks.
See, what I'm using is this. This is one vector space. If V is of dimension n, this is another vector space. And matrices serve as a linear bijection. And it preserves products. Wherein the product over here is composition and over here is the usual matrix product. So that's the big tool that I am using. So every matrix is actually the matrix of some F for a unique F. Matrix of F for a unique F. And hence the first two lines are therefore equivalent. That's the whole story. So you see the intricate connection between coordinates, matrices, linear transformations. Okay, so these are the intricate connections and very, very intrinsic, and that is at the heart of this whole course. The notion of coordinatization, the notion of linear transformations, and hence matrices. We'll be using this linear bijection of matrices right and left to shorten our computations, to see what is going on. We'll be doing this again and again. So you should get used to this back and forth shifting between linear transformations and matrices. That's what I'm trying to emphasize always. Don't get into computation from the first slide. Stand back and think, what is this saying? Sometimes doing it with linear transformations and vector spaces in general might be much more easier. You can deduce it much more easily than doing a raw computation. So don't go for computations. That's the whole idea of this.
So, sir, they were not asking me to computate the two squares. They were never asking me to computate.
Yeah, you don't compute.
Thanks, sir.
Please ask you something.
Yeah?
But it's not like about words.
Huh?
Is this Mr. Ghosh?
Yes, what is it?
Oh, sorry. So when you were in the university second year for linear algebra, which textbook did you use?
Well, those textbooks are available still now. You can get it on the net. And this and is not commutative. MacLean and Birkhoff, this and is not commutative. MacLean and Birkhoff is not the same as Birkhoff and MacLean. There's also a book by Birkhoff. Birkhoff and MacLean is different. I'm saying MacLean is the first author, MacLean and Birkhoff. I think the last reprint of this was done in 1997.
So would you
And this one is a print.
So would you recommend them?
Yes, yes. If somebody really wants to learn algebra, and obviously there was another book which was not a textbook, but it was something like a storybook kind of a thing. If somebody wants to learn algebra, well, these books are possibly the best resources.
The best.
The best resources. You can see the time from which it has.
So can I please ask you something? How do you remember the names?
Well, these are, well, what do I say? Do you forget the name of your Bible?
No, oh, okay, okay. So you studied a lot, so that's why you remembered it.
I missed this one on kernel and drive.
Oh.
What available? Yeah, because can you just explain a bit about the kernel?
Which one?
The kernel. Because I missed the
kernel
lecture.
Okay, so suppose you take a linear transformation. The dimension of V is n, is finite, and you first start, the first step is, so the kernel of F is a subspace, so its dimension is less than or equal to n. Now, if the kernel of F is 0, there is nothing to do, immediate. If the dimension of kernel of F is 0, so this is just saying that F is injective.
Okay.
And hence, for any basis, let's say if you take a basis B, basis here, FV1 is a basis for image of F, and hence